Good morning to everyone. Myself S.R. Balaprasan, final year department of ECE, Coastal Engineering College, Savagasi, Tamil Nadu, and my mentor name is Dr. A. Kamran, Associate Professor, Department of ECE, Coastal Engineering College. Our paper title is Portable Leaf Disease Detection and Lung Cancer Detection using Deep Learning Techniques. Our main objective is to detect the disease that affected the portable leaves, namely blight diseases like early blight and late blight, that is the early stage of a blight disease and late stage of a blight disease. We have also used we have used the CNN model to predict the disease that affects the plant, and we have used the same architecture that we used in portable leaf disease detection in lung cancer detection also. So we created a model to predict the lung cancer, that is three stages of lung cancer with a normal stage. So totally four output classes will be there using the deep learning techniques. In model 1, the portable leaf disease detection, we have used the CNN to array to our prediction model. Here we have used CNN to extract features to predict leaf disease. That is important features to be extracted in order to help the prediction model to predict the disease that been affects the leaf. So in this model there are 6 layers, that is 6 layers of convolution layers and followed by a dense layer. In each layer there will be a convolution layer with an activation function, that is a ReLU function, followed by a max pooling layer in order to select the maximum value within the filter area. After the 6 layers, there will be a flatten layer which will flatten, that is, it will convert all values into a single array, which will then fed into a dense layer. For a dense layer with a softmax activation function in order to predict the probability distribution of the 4 classes. And from the 4 classes, the maximum probability class will be considered as the predicted output. It is the architecture. Here the first we have given the input shape of the images 256 cross 256 cross 3, that is with 3 channels, and the filter size is 32. That is a batch size is 32, followed by here we have undergone many pre-processing like random flip and rescaling the image to the required image size and normalizing the images. These are all the pre-processing techniques we have carried out, and the random rotation is used to make the model more prone to any type of photos in order to arrive at correct accurate precision. Here there are 6 convolution layers. In first convolution layer there will be 32 filters, and here there are 896 parameters has been got. It is like in the previous model. Here we have used 3 cross 3 filter area. In our previous layer there used 3 filters, so 3 cross 3 into 3 we get 27. Into the present layer convolution layers filters number of filters is equal to 32. So to multiplying all these 4 we will get arrive at 896 parameters. In this way all 6 layers the consecutive parameters are derived. And followed by convolution layer as the max pooling. In max pooling, we have used a filter size of 2 cross 2 and size of 1. And convolution also we have used the size of 1. So in max pooling, within the 2 cross 2 area, the maximum value within the area is chosen as the output value, and it helps to form the new activation matrix. In this way the 6 layers proceeds, and after the 6 layers there will be a flatten layer which will flatten the values which is in the matrix form in the previous layer into a single array, that is 2 into 2 into 64, which will give us a 256 out of 32 batches. So 32 batches of 256 values. After that it is fed to a dense layer. We have used a ReLU function. The ReLU function is nothing but which will make the values. If it is greater than 0, then the value is same as it is. If it is less than 0, then it is considered as a 0. After that, it is again fed into a dense layer where we have used the activation function of softmax, that is a probability distribution, in order to find the probability distribution. Here in leaf prediction we have used 3 classes: normal, early blight, late blight. So since the three classes are being chosen, we have given output classes number is equal to 3. So based on the probability distribution of the three classes, the maximum probability distribution is chosen and is given as the predicted output. In this last dense layer, it will give us the probability distribution of the three classes. Activation function. The activation function decides whether a neuron should be activated or not by calculating the weighted sum and further adding bias to it. Based on the weights, it is decided whether the neuron has to be get fired or not. If the neuron fires, it will give the output. If the neuron that is not fired, it will become calm. So here a ReLU function is used. ReLU is a rectified linear unit function for which the f of function is x for x greater than or equal to 0 and 0 for x less than 0. It is as I already said, the value will retain if it is greater than 0 or it is become to 0 if it is less than 0. So all negative values have become 0. Compilation. The optimizer used here is ADAM optimizer. Adaptive moment estimation is an algorithm for optimizing technique for gradient descent. A gradient descent simply measures the change in all weights with regard to the change in error, the slope of a function. The higher the gradient, the steeper the slope and faster a model can learn. If the slope is 0, the model stops learning. So here we have used ADAM optimizer. The method is really efficient when working with large problem involving a lot of data or parameters. It requires less memory and is efficient. This algorithm uses two types of algorithms, momentum and RMSP algorithm. First, the momentum formula is Wt plus 1 is equal to Wt minus alpha mt and mt is equal to beta mt minus 1 plus 1 minus beta of dou L by dou Wt. Here it is nothing but the Wt plus 1 is the weight to be calculated and Wt is the previous weight. Wt is a current weight. The Wt plus 1 is the weight to be calculated and alpha t is the learning rate at time t. Dou L derivative of loss function and dou W is the derivative of weights at time t, and beta moving average parameter which is a constant value. RMSP, root mean square propagation. Root mean square propagation RMSP is an advanced adaptive learning algorithm. Here it is also same as like that. Here the W, in order to find the weight Wt plus 1, the previous weight is used along with the learning factor and the Vt value. Wt means weight at time t, W plus 1 means weight at time t plus 1, alpha t learning rate at time t, dou L derivative of loss function, dou Wt derivative of weights at time t, Vt the sum of squares of past gradients. It is that the previous steps, how many steps has been got by the gradient, so it is all calculated and the overall sum is given as a Vt up to time t. Weight of the moving average parameter, as I mentioned, it is a constant. Epsilon is a small positive constant 10 power minus 8. Here mt in order to find the present weight, we have taken the values from the previous records and it is calculated as so, and based on that value the ADAM optimizer will optimize the weights to be assigned to neurons in order to avoid the overfitting problem. Loss function. In this model, loss function used is sparse categorical cross entropy. Since here the number of output classes is not represented in one-hot encoding, rather it is represented as integer index. Here binary cross entropy cannot be used. So the sparse categorical cross entropy is used. The cross entropy is a measure of the difference between the two probability distribution. Here the cross entropy is there is more than 2 or 3 output classes. Then based on the probability distribution of these all classes, the output is predicted. So in order to assign our probability distribution, the probability distribution is calculated by the difference between the actual value and the predicted value. So based on the difference between these two, the probability distributions are calculated, and based on this output is predicted. Sparse categorical cross entropy. Sparse categorical cross entropy loss function measures the difference between the predicted probability distribution and the actual probability distribution of the target variable, as it said so. Metrics used here. Accuracy is the metrics used here. Metrics are used to monitor and measure the performance of a model and don't need to be differentiable. It does not play any role in weight modification. Accuracy is a metric generally describes how the model performs across all classes. The accuracy formula is true positive plus true negative divided true positive plus true negative plus false positive false negative is all positive predictions divided by the total number of predictions. Yeah, it is the datasets we have used, that is for leaf disease detection. That is separately training, testing, and validation dataset, each with late blight, early blight, healthy leaves classic classes. Overall, these datasets counts to around 4072 images. Result, using this, we have arrived at a result of around 96.5% accuracy, and it is attained in the faster mean. In order to, since we have optimized the architecture, the model runs somewhat fast, so we got almost at 96.5% accuracy when compared to other models. Model 2, the lung cancer detection. Here in this model, we have used the same architecture as the leaf disease detection, and same max pooling layer and the same activation function and same 6 layers of convolution, but we have changed the image size and some other pre-processing techniques we have used so that we can arrive at a somewhat better output. Dataset taken from Kaggle. Architecture is same as that. At last it has 7 batches of 4 output classes. The result, we got almost 95% of accuracy, and we are about to enhance it further. Since it is a medical field, we have to achieve almost 99% accuracy. Thank you. Now I